All right, so the best part of calculus, finding derivatives, is here. So let's dive in and start out looking at the power rule for taking derivative. We are still continuing to study about derivatives, but now I am introducing the power rule and some other basic rules to find derivatives. All right, and so the reason I was saying that this topic we're about to start here, and as a matter of fact, this is the beginning door into the fascinating part of taking derivative right there. And so we have seen up to this point that a derivative can be regarded as a function. So if we have a function f of x given a function f of x, then we have learned, we have studied, we have learned through the previous video lecture that f prime of x now is the official symbol for this is the general derivative, or for short, just the derivative of this function at any general input x value. And we have done, we can find this general derivative of f of x by taking the limits of the difference quotient f of x plus h minus f of x and divided by h. And we take the limit as h goes to 0. So a few more times I'm going to keep re-emphasizing this because this is the fundamental, this is the foundation of all derivative formulas that we're about to learn from this moment on. Okay, so it's whatever I'm about to introduce after starting in this video lesson. Even though we've learned very nice technique, we learned really nice formulas, but this formula is the origin of any of those formulas that you're about to learn. Okay, so don't get me wrong that we're gonna completely forget about this formula. It's just we're gonna find more efficient way or more effective way to find derivative quick and effectively. All right. And so now, let's start out with a few problems and to motivate the idea. And it's not even an example. So here I am just going to, let's say we want to find the derivative and find f prime of x with different functions. So here is just, once again, remind yourself from what you learned in the previous video lecture that this is just general derivative on relative to whichever corresponding to whichever function that you have that you are given. So how about when f of x, and to clarify, how about find f prime of x if, okay, and now I'm going to start out given, all right, so x squared. So for this problem, we have seen that so many times since in our earlier lecture, in our earlier video lecture, so there's no need to make everyone repeat. So I'm gonna, for this particular problem here, f of x equals x squared, we have found already, and if you're feeling shocked about where I got this result, then you can roll back to my previous video lecture on how we carry through the limit definition and found the final derivative on this. So f prime of x, if f of x equals x squared and f prime of x equals 2x, we already found that result. And now I'm putting it here in a column. And of course, for any viewers watching this video along, make sure take notes, and especially I am going to be repeat, the similar problem, but for quite a few other functions as well. So how about I am going to push that into f of x equals x cubed. Okay, so here we have f of x equals x cubed, and the main aim of the problem here is to look for f prime, the general derivative of this function f of x, where this time we switch from x squared to x cubed. Okay, and so at this point, if we have done this problem already in earlier video lecture, or we have not, let's just start all over again. So I am going to invent, or I am going to discover what the general derivative of this function would be. So f prime, and like I said, the limit definition will never be left behind, because we will always have to use it anytime that we discovering a new derivative or the derivative of a new function. So I am going back to the to the zero ground right here, and this is what I call zero ground. It's the very original starting point of finding any derivative. F of x plus h minus f of x, okay, and divided by h. And we have limit as h goes to 0. And really, it's a high recommendation at this point that since for any viewers here, I'm doing this step here as a step to discover the derivative of this x cubed. So I recommend that as you're going along, you can just simply write these steps right here in scratch work right here. Because really my main aim is just to, after we'll be going through a whole bunch of steps, but after we're completely done with all the steps, we're gonna just focus right at the final derivative of this function. So that means in the next step here, our function currently is x cubed. So f of x plus h, once again, as you have seen this work so many times, I am going to substitute x plus h into our function, and our function set x cubed. So here x plus h all cube, it's a cubic function, and minus f of x, which remains the same, x cubed. And we are dividing this by h, and we take limit as h goes to 0. Okay, and so in this way, now let me switch to the other board. So right from the very previous step right there, then I remind anyone viewing this video again that the high power cube right here, that cubic high power for that x plus h being cubed, easiest way is to think of that as x plus h times x plus h times x plus h. And we're going to start foiling it out, foiling all that out. So of course, take your time, pause the video. You are more than welcome to pause the video if you have to give yourself some opportunity to get caught up. And so at this point, for that particular cubic right here, then factoring it out is going to give me an x cubed, and I'm particularly talking just about this x plus h in parentheses cubed for now. So x cubed plus 3, okay, x squared h plus 3x h squared plus h cubed. Okay, so that's how we FOIL out and combine all the like terms, and this is what we should ultimately end up with. So we are now going to substitute this for our expression from the very last step. So from our very last step is right here, where x plus h in parentheses cubed now is going to be replaced by this. And so in that way, here's my next step looking like. X cubed plus 3 x squared h plus 3 x h squared plus h cubed. And as we go along and keep going further into calculus, I highly recommend that review your algebra skill, your algebra fundamental, so that you can get any of these understood easily. Now we take limit as h goes to 0, and none of the steps we've been doing so far is safe to apply limit laws directly. So in that reason, I am going to continuously simplify my expression. And so here in that way, I have opposite terms here. So opposite term here. Okay, so my next expression is going to be 3 x squared h in the numerator plus 3 x h squared plus h cubed over h. And we're taking limit as h goes to 0. But still, this is not safe to apply directly the limit laws, meaning we're trying to make it look like we're substituting h equals 0 into the expression. It's not safe yet. And so we can simplify further by recognizing that we are having a common factor h here again. So all that work should be very familiar. So I have to constantly remind all of these work so that in the next problem I am going to be able to pick up the pace a little bit more. So common factor h is going to be factored out. And now we're looking at 3x squared plus 3xh plus h squared. And that's the result after pulling out that common factor h outside of parentheses. And we still have that h in the denominator. And of course, our problem still remains as a limit problem because we haven't done any limit work really. And so now, the common factor h in both numerator and denominator will get canceled out. And so our resulting expression now is going to be limit as a problem, as a main problem, but we haven't done any of that yet. Our expression keep being simplified down, so at this point we're looking at 3x squared plus 3xh. I need to leave a little more space for myself, plus 3xh plus h squared. And then I have explained so many times in my previous video lectures that, so now when it comes to this, it is now safe. But notice again that the expression involves two variables, but only the h now is our primary variable that when we're letting h, when we're approaching h to 0, then it's going to affect these terms right here. 3x squared is, in other words, independent with h. And so in that way, as h gets closer to 0 under the concept of limits, first term independent with h remains exactly the same. So we're looking at 3x squared for the first term. As we let h getting closer to 0, then 3xh here is going to get close to 0. So I have a final limit for that term here being a 0. And now as h gets close to 0, the entire h squared according to limits law become another 0 or 0 squared. So in that way, our final limit is a 3x squared. Okay? And so go ahead and take notes or pause the video, because I am going to come back to the other board and nail down an important result right here. All right, so back to my other board. And as I said earlier, all of this work here, even though so many steps, but I apologize for wasting all your effort so far, but we don't need any of these any longer. The point now is that the very final result we have found that you just saw a moment ago. This is our final derivative of the x cubed function. And so if f of x equals x cubed, then we have found its derivative, 3x squared. And there's a reason why I'm putting these results in separate columns with sort of parallel results right here. So viewers and students of mine can start observing, and we're going to start recognizing a better and a more effective methods to find derivative. Okay, so let me challenge you with how about f of x equals x to the 5th power. Okay, and so we want to find f prime of x. All right. And so with this little narrow space of my column right here, I don't think it's enough to fire up the limit definition, but let's save all that limit definition for the other board right there. So I am now moving to the other board. And let's have a moment erasing my board up here again. All right, so definitely to find that derivative, and this time keep in mind our goal is to find the general derivative for the x cubed function. F of x equals x cubed. And so again, the famous starting point where I so-called at the zero ground, we have to use it again. So what I need is f of x sub 0, x plus 0 minus f of x divided by h. And we are going to famously take the limits as h goes to 0. But now, since our function this time is the x to the 5th function, then I am going to substitute the x plus h expression into my 5th power. So here I'm looking at x plus h raised to the 5th power minus x to the 5th. Okay. Take your limit as h goes to 0. And of course, don't forget we need to divide by h right there. Okay. And so once again, to move on to the next step, yes, anyone who would like to go this route right here, think of the x plus h as x plus h times x plus h times x plus h 5 times. Maybe I shouldn't even leave the dots there. Let's just write it down completely. X plus h, okay, times x plus h. 5 identical factors. But now the real challenge here is how many viewers are going to be willing or patient enough to FOIL out, even though you could. I mean, if you have enough time. Okay? So at this point, when the power is starting to get high like this, I mean beyond 3, then we start thinking of a little bit more effective. But that does require some of your algebraic understanding a little bit. So back in the days that you've learned algebra, and I don't mean to keep reviewing too much algebra, but calculus, over 90% of calculus is heavily based on the algebra work. So there was a famous identity back in algebra that we call the difference of powers. The difference of powers. I'm talking about two same powers, two terms being raised to same power, and there's a difference between them. Okay, so maybe I am sure that you have seen this in your algebra courses, but maybe your teacher never emphasized that. It's okay, completely understandable, because there might be not too much applications back then, but they're here. It's surprisingly become so useful for us. So generally speaking, for any power n right here, you can apply that to squares. That gives you difference of 2 squares, cube, difference of 2 cubes, or 5th power, 4th power. What we have here is a difference of 2 powers, power 5 right here. So generally, we are always going to have that. So when you're looking at the difference of powers of 2 powers, then we always going to have that first factor being a minus b, but completely without the 2 powers. So only a minus b, the difference of a and b. And then you are going to put that into a factor form with another factor. Here is a times a raised to the n minus 1 power plus, and only one lonely term, plus a, and now we're going to reduce the power by 1 more, so n minus 2. But now we're going to start having a power for b, power 1. So in that parentheses, here's the way. A to the n minus 1 plus a to the n minus 2 times b. And my third term, my next term, is going to be a to the n minus 3. So the pattern here is we keep each term in our big parentheses here, we're going to keep reducing power by 1 in each step. And then as we go along, and we're going to keep increasing. So it was power 1 for b here, then here is going to be power 2. We're going to be repeating that until we reach to the end where the power of a reduced completely and become power 0. So no more a at the last term, but it's now b to the n minus 1. Okay? And so, and maybe I didn't give a very good explanation of this, but there are tons of Google resources out there that delivers explanation about this difference of two powers. So if my explanation here didn't convince you, this is only a review, so you have tons of resources out there to have a clear, solid understanding of this. But now, how we use that here in this particular problem? So now allow me to bring that into the next step, and we're going to apply. So as I said again, that anyone who decides, anyone who feels that learning or reviewing for yourself about the difference of 2 powers is a little bit too much, then that's fine. Stay with your foiling out, you will get the exact same answer as mine. Maybe just your steps is a slightly different route with mine. But now it's a limit work. Recognizing that this is the difference of 2 power 5s, I am going to, see, the first factor is x plus h, no power, minus x. These come straight out from the difference, but these two terms, no power. That's why I have x plus h minus x. And then I'm going to open a pair of brackets here. And so my first term was originally x to the 5th, but now it's x plus h, the entire term, but only to the 4th power. See, so after factoring it out, then in my big parentheses here, the first power already reduced by 1 compared to the original version. And then, but no other term. I mean, no other factor. And then next, it's all plus. X plus h to the 3rd power. But now we're going to start multiplying with x. Okay, so there's no x here, meaning x to the 0 power, and then now x to the 1st power. But then the x plus h terms reduce power in each step like that. And so I'm going to have another one. So here we're looking at x plus h to the square power. So we're reducing the power. And here x now is becoming square. The other term now is start increasing power. So we're going to keep repeating this until the very last term, no more x plus h, but now only contain x to the 4th. Okay? All right. So, and I don't even need anyone following this video to FOIL out any of these. That's because that's the point. Let's just keep them the way they are. Just note that each one of these has the h variable involved in there somehow. In the end, we're still going to divide it by h. Okay? And this is going to take limit as h go to 0. So now, in my next step, of course, think about in the first factor right here, then it's right in front of me and hopefully right in front of anyone viewing this video. We have opposite terms here, so we can cancel that out. Okay? And so our first factor now is reduced to h. And all that big one in brackets still there. X plus h to the 4th plus x plus h cubed, because we reduce the power by 1, times x plus, and now x plus h square, x square plus, how about this time I have a little more space, so let me just write it all down. This is x plus h to the 1st power only, but now x cubed plus, and the last one now, that goes to power 0, so no more x plus h. This is now x to the 4th power. Okay, and all divided by h. And we'll take limits as h goes to 0. Okay, and so in that way, common factor h is cancelled. Okay, the common factor h got cancelled away. And so here we're looking at, after canceling that, then limits as h go to 0 become only on that something that's only effective for that x plus h to the 4th power plus x plus h cube x plus h square times x square plus x plus h plus, times x cubed plus x to the 4th power. Okay? And notice that we're actually having 1, 2, 3, 4, and 5 terms. So, the real good part is here. So now at least what I know is that it's safe to substitute in because limit laws now can be applied. So I have to keep emphasizing we're not really substituting, but it works like we're substituting because of the limit laws. So we can think about substitute h into each one of these. So that makes the first term, if h becomes 0, if h goes to 0, first term becomes x to the 4th. Okay, and go ahead and pause my video if you have to. Next term, as h go to 0, give me x to the third, but times x. X to the third times x is another x to the fourth here altogether. So all that here is what this second term becomes as h came closer and closer to 0. So same thing, third term, as h got to 0, got closer and closer to 0, then the whole term came to x squared, but x squared times x squared is x to the fourth again. And the fourth term is similar behavior, but that becomes another x to the fourth, because as h went to 0, approaches 0, then that becomes x, but x times x cubed is an x to the fourth. Last term is completely independent with h. So last term remain x to the fourth on its own. Okay, and so what we found here, and the reason I really have to write so my work here is so squeezed together because I want to save all the 3 other columns there on the board without any modification. And so now all together, these are all like terms. So combining like terms, we're looking at 5x to the fourth. Okay, so much work, it's worth our time, even though I am now just gonna throw these away, because all we need now is so much work to arrive at this useful answer right here. All right, so I am now going to put that final answer here. When our function f of x was x to the fifth, then our derivative we found was 5x to the fourth. Okay, so 3 problems right on the board is now good enough to start recognizing a generality, and then from that generality, or we can see that, or we can think of that as a pattern. Once you recognize that pattern, it becomes the rule that we can apply. So here's the thing. Whatever you already had in mind, just hold it. These functions, first of all, these functions, they are in the form of the variable being raised to a power. See, variable x, the main variable of the function, being raised to a power. Same way here. This is the variable being raised to a power 3. This is the variable being raised to power 5. I could have done the problem I could have also done with that problem f of x equals x to the fourth as well. But if I did that, then it's a little too close to these, so you probably think that I had some intention. I mean, of course I had some intention, but I want you to be a little more flexible in terms of these power. Okay, and so those are the powers. And look at their result here. So when a power was a square, f of x equals x squared, and our final result as a general derivative was 2x. Now, I have to explain again, even though it's only an algebra thing, but 2x here, without a power displayed here, it really means power 1. Okay, so 2x to the first power. So think about the relationship here, and 2 here looks like that power 2, but now in the derivative version. So original function, the power is 2, but now in the derivative version, when we came to the derivative, it looks like that coefficient 2 is exactly the power that was before we took the derivative. And now we still have a power here, but the power is reduced, being subtracted by 1. So from power 2, we subtract 1, we get 1. So that's something we recognize. Something we recognize right out from the first function here in our first column. Let's see if it's the same in this middle one. When the function f of x equals x cubed, it's a power, okay, variable raised to the power 3. And so now this is our derivative. The coefficient in front of our x squared here is a power 3. I mean the coefficient 3. It looks like the exact number with the original power. So 3 here is the power that was originally there with our function. And the power 2 this time, once again, what we see here is perfectly consistent with what we recognized earlier in that one. The power 2 now in the derivative is the power 3 previously minus 1. The power 3 from the original function minus 1. Okay? And so we're starting to feel a little more firm about this. And so check that out again in the third one right here, in the third column right here, to see if once again it agrees. So x to the fifth, this is a power function in a sense that your input variable is being raised to a power of 5. And so look at the final derivative we have found right here. F prime of x equals, so now we got a coefficient 5 in front. Think about where that came from. It did come from that original power, didn't it? Okay, and the power of 4 that's now current for our f prime right here. That power of 4 came out from power of 5 originally from the function. But now subtract 1. Okay, so now that should be enough for us too. So I try to stay away from a formal proof because proof is safe for people who are going for a formal math major where it's going to take an advanced course to understand. But here, just directly recognize from the pattern right here, we can draw a really good conclusion. So what is that conclusion there that we're looking at? Okay, so it looks like if f of x is some function x to the n, okay, f of x is some function x to the n, then f prime of x, okay, pause the video, make your own prediction of what I'm about to write, and then as you resume, I'm going to write and see if you agree with me. All right, so I hope you had some prediction on your own about a generality. We're about to make a discovery here. All right, but if f of x is if f of x was a power function, then f prime of x is going to be the power n, is going now in the derivative version, becomes the coefficient, and still involving a power, but now power n minus 1. Okay, so ladies and gentlemen, what we have just recognized here, what we have recognized just now is the famous so-called the power rule. Okay, it's the power rule for, and see, this is the reason why the rule for taking this kind of derivative is being named the power rule, because it's particularly applied to that family of function where it is a power, some power of x, okay? So that's the power rule. So let's now, once we have done that, let me now mention some other notation used right here. The way how we use notation to make things convenient for us for the rest of our study in calculus. Okay, so what I'm about to say now is that, see, the entire problem I was doing, and including any problem we have seen in previous lectures, then in these days now, commonly you're going to see this instruction. It's an instruction. The instruction of a lot of problems is to start out saying in word, find the derivative of f of x. That's in word being spelled out. But a shorter way of saying is find f prime. Okay, that's one way of saying that. See, or people can say find dy dx, and you already knew that these are all different symbols of derivative depending on how you write your beginning function. But now, even shorter than that, now I'm talking about I want to come up with a symbol that it's even more convenient than just saying find, because see, when you see this, it's an instruction telling readers to find the derivative. So this is the derivative of the function f in respect to x. Find the derivative of the function again, where the function was written as an equation y equals some expression of x. But now all of this here is still long. Okay, so we need to come up to even a better way. But this way I'm about to write is more like an instruction. So now if you have a function f of x, okay, versus a function written as in equation formats, y equals some expression of x, for example. Okay, there are just function, could be even the same function, but different ways of writing it. And so, yes, at this point, anyone is knowing and well familiar that so if your original function was in functional notation, then f prime means the derivative. Okay, but now this statement, particularly this statement, find f prime right here. Find f prime. This statement can even be conveniently written symbolically as, so here's your function, but I want to instruct whoever looking at the problem. So this symbols, so outside of your function, I'm going to put a pair of parentheses and put a prime there. Okay, this is an instruction. It replaces all that worded statement right here. So this says, this instructs anyone to find the derivative of the function. But here we don't even need for, it's just mathematicians. We love using symbols. We try as best as we could to replace the wording with symbols. Okay, and so this whole symbol, the way it is, it's an instruction for anyone reading it. It says, find the derivative of that function. Okay, and so same way, if your function originally started out in the form of an equation where one single y then equals an expression of x, some expression of x, then of course everybody already knew that the dy dx means the derivative. But so a lot of time when we're actually being instructed to do problem, then the instruction says find dy dx. Okay, so all that here is equivalent to, okay, so your expression, okay, your expression of x, of course, but people are going to attach the symbol d that stands for find the derivative in respect to x right here. So this is an operator or an instruction telling people, hey, find the derivative, treating x as the main variable on that whatever function written here as the expression of x right here. Okay, and so a quick usefulness of that. Let me erase the other board and we're gonna move over to the other board. All right, so for example, if the problem we've had earlier, instead of saying find the derivative f of prime of x, if you see f of x equals x cubed, so much writing. Here I'm only discussing how we can write one instruction to instruct people to find the derivative. So this is what we did. I mean, this is what I'm going to apply here. So the function was started out in functional notation. So I'm going to indicate directly. So our expression right here. So x cubed is our function. I am going to do this thing, prime. Now we can completely disregard all this. Because seeing this right here is one instruction telling reader everything. Take the derivative, find the derivative of the respective function x cubed. So now the answer to that is 3x squared. See, instruction what to do, and now, or see, the derivative of, and all that, and equals to 3x squared. So that's one way of writing that. Right? So now enough with the discussion on notation used right here. Let's get back and continue our study further. So before I get any further on the power rule, allow me to look back and have everyone viewing this video recognize a few other things and see how this power rule already lived in a lot of our problem we did that we can recognize. So for now, let's put a pause to power rule right now. Let's start out with our function being, okay, f of x equals a constant function. And now I'm not going to write 5, I'm not going to write 1,000, I'm not going to write -3, -10, whatever. It's just simply a constant. Our function is a constant, meaning doesn't matter what x value is, regardless of whatever x value is, our function output remains c for whatever c is being defined here. So we want to find the derivative of this function. Okay, so we want to find the derivative of that function. And so one more time, I'm asking viewers to follow, and my students to follow along with me. Let's go back with the limit definition. So even though I just now showed the power rules, but some of you might recognize how to use a power rule, but some of you might not. It's okay. In case where it's still such a huge debate, huge struggling in your mind of whether we can use a power rule here or not, that I've just finished showing everyone, we can always go back to the ground zero or to the zero ground. Okay, and what do I mean by zero ground here? F of x plus h minus f of x. Okay, and this should come quickly and be finished easily. Okay, this is always a zero ground for finding any derivative. And so now, but your function, since being a constant function, so regardless of whether you're substituting in an expression or a number or a value, the output is always c. So in other words, what I'm trying to say is f of x plus h must be c, or the output, and so is f of x. The output for f of x is also c divided by h. Okay, it's just that famous quotient right there. And we're taking limit as h goes to 0. It's only the second step so far. C minus c, they're opposite terms, so we can cancel those out. Okay, and so consequently we're ending up with 0 divided by h. Taking h goes to 0. So keep in mind again, we're not plugging in 0, but we're letting h getting smaller. So no matter how h getting smaller to 0, it's still in the end, it's not equal 0 at the denominator, but 0 divided by something that will never be equal to 0 is a 0. So you don't even need to take a limit. Your final limit here is 0. Okay, what have we found? 1 step, 2, 3, and only 4 steps. We already found an answer. Okay, so now generally speaking, after all that results we have done, and I worked particularly on the function being a constant function. So now here's one way I can express that, or maybe let's not be too rushed. If we have a given function being a constant function, f of x equals c, then famously the derivative of this kind of function will always famously be 0. Okay, maybe this is only the first time today we're recognizing this, so it's probably a little new for anyone, but trust me, it will stay with you as you see that oftenly enough. Okay, so if your function is a constant function, f prime is going to be 0. So now, in the way how I just showed the notation usage earlier, then here's even a more convenient form. One instruction and anyone is going to understand. Your function is a constant, and we're taking the derivative on a constant. Okay, your function is a constant, and taking the derivative on a constant. Then, see, one formula. Take the derivative of a constant c. The answer equals 0. Another way of seeing this, you have a constant and you take the derivative in respect to x. It's a different way of writing it. Derivative in respect to x of the constant c is 0. These are all 3 different ways. The long worded way, and these are the 2 short symbolic way of expressing, but in the end, this is the rule about derivative of a constant. So some textbook authors call this the constants rule, Some the people call that the derivative of a constant. You can call that whatever. Okay. This is derivative of a constant. All right, the derivative of a constant. Okay, but now at this point, I'm sure there are viewers who are not convinced with what I'm teaching here, with what I'm delivering here, in a sense of, we were just before at the beginning of this video talking about power rule. How is this connected with power rule that I'm putting right here in my lecture, and especially immediately after I've finished showing the power rule? Okay, so I will be able to give an explanation about that rule again under the point of view of a power rule shortly later, after we've gone through all the basic other basic rules. But for now, let's continue on right here. So now back to our understanding of the power rule. Okay, let's see how useful the power rules can be. All right, so let me now start bringing viewers into example 1. All right, so yes, let's find the derivative f prime of x, okay, or dy dx. Okay, and I'm going to be giving out different function for all of us to find the derivatives together. So here, how about part A? So let's look at f of x equals x to the 100th power. It's a power function. Okay, the input variable here is being raised to a power 100. Okay, and so at this point, the whole point of learning the power rule is that we do not want to do this. We don't want to do f of x plus h to the, f of x plus h minus f of x divided by h, and then consequently we ending up with the difference of x plus h all in to the 100 minus x to the 100 divided by h, and take limits. I have to yell it out loud again. Yes, this is the legal work, the correct work. Nothing wrong with that. The only thing wrong, it's going to take a lot of time. It is going to take a lot of time. So we don't want to going that route anymore. The whole point of recognizing the power rule is that, so now, and we formally have proven it. And so that means now our f prime of x can just simply be the original power was 100. So now when we get to the derivative has to be x to the original power subtract 1. So 100 minus 1, 100 minus 1. And for starter, I highly recommend write in a way that the power originally minus 1. Okay? And then that original power also be multiplied in front as a coefficient. Okay? And so now your final answer for the derivative of the x to the 100th power function is 100 x to the 99th. You have found another big derivative out there. Okay, the derivative of something very high power. Okay, and so let's look at part B of the example. So how about, let me point out another shock for anyone. So everyone, after seeing example part A of example 1 right there, it's been, maybe you start thinking probably the power x to the n minus 1 times n is only for the, you see, x to the n, take the derivative, equals that. So maybe you're thinking that the power is only for, this power rule is only for the integer power. Let me show you a surprise. Y equals square root of x. I'm sure we have seen this derivative somewhere here and there in our previous lectures, in our earlier lectures. But let's reinvent the whole thing and see how the power rule can be extremely useful for something like this. So, but it does require your algebra understanding a little bit. So from start, at start, we don't see a power written out so trivially in this problem. I mean, it's a square root. And I don't see any, like, it's not like an x squared, it's not like an x cubed or whatsoever where the power is so trivially written. So here we have to purposely display, and you got my word right there, we have to purposely display the power nature of a root right here. So now this is before we take the derivative. Before we take the derivative, I am going to rewrite y equals square root x as y equals x, but to the power 1/2. That's the nature of being a root right there. Square root can be understood as power 1/2. So generally speaking, another algebraic reminder right here, but nth root of x is the same as x to the 1/nth power. Start taking that with you right there. Okay? And so in that way, so now I'm ready. So here it's just, here, this is not, I have to make clear again, this is not the derivative. This is just a place where I clearly show that what we have there is a power function. Now the power rule is ready for action. So I'm going to say dy dx equals the power subtract 1. So it never hurts to write it down for the first few times that you are starting to learn about this. So 1/2 minus 1. And then we're going to do the math later. And the original power 1/2 also is also multiplied in front as a coefficient. So now our final expression is going to look as following. 1/2 x. 1/2 minus 1 is anyone, please. You are at calculus. You are expected to know what a negative power means. So 1/2 minus 1 is a negative 1/2 power. So you do have negative 1/2 power. So for me, normally when I'm seeing my student written work submitted to me, I'm fine with displaying the final power as a negative power. I'm fine with that, but some other instructor might not. So here's another way of re-expressing this. So now I'm talking about you already found your derivative at this point. I'm personally fine with my student submitted work to look like this, but in case that you have some instructors that expect you to know how to clear out the negative power here, then the negative power makes the x power here going into the denominator. So you're looking at 1/2 times x to the 1/2 power. Okay, that's one. See, but now when you put your power in the denominator, make sure it's now a positive power. That's another way of accepting written work right there. And even some instructors expect further in the students. Some instructors want their students to be able to re-express this in terms of a square root. So that same answer, 1/2, but square root of x. 3 different ways of writing your final answers, depending on how high your instructor is expecting your work. Okay. And so, like I said, like I expressed earlier, I'm normally fine with this because it's as long as it shows my students know how to take the power rule properly, I'm fine with that. And doing these, it all depends on how comfortable they are with their previous algebraic understanding. Okay, and I don't want to make it an overpressure for any of my students. All right, so that is example 1, part B. But let's not be done with that yet. Let me now introduce part C, a slightly more advanced form of these of how you can apply the power rule here. So what about so I'm getting tired of f of x to be the name of the function. So how about g of x? So the derivative version has to be g prime of x instead of f prime. Okay, and so how about x? How about square? Okay, times square root of x. Okay. So it looks completely scary at first, okay? But once again, and well, there's maybe a power here, but crazy going with square root and all that. So here's the thing. Once again, before we can apply the power rule, we have to find our way to re-express this so that it completely displays only one power. The point is 1x to 1 power. Not like this is a product, 2 separate powers. Not cool, not cool. And so in that way, how I'm explaining, notice again that there is a multiplication here. It's a product of x squared and square root of x. So x squared already has its own power clearly displayed, but the square root x here must be rewritten as a power 1/2. So x squared times x to the 1/2. So all together, this is algebra review again. X squared times x to the 1/2, same base. So whatever power here, we're going to add up the powers. So your overall as a power function is x to the 2 plus 1/2. Okay, and 2 plus 1/2 is a x to the 5/2. That's our actual power right there. Okay, and so now g of x. So again, I have to make clear, this is before we can take the derivative, but I have to successfully turn my expression into something that involves a single power, one single power. And so all that there equals, gives me g of x equals x to the 5/2 power. And so now the derivative worked, and to apply the power rule is now ready. G prime now is, once again, it never hurts to write it down in a couple steps. Right here, 5/2 is the original power. Now in the derivative, we subtract 1. Subtract 1. Okay? And then the original power now in the derivative becomes the coefficient in front. Okay? And so now all together, it's a 5/2. Okay? And 5/2 minus 1 for the power here becomes, it's going to be 3/2 right here. I'm good with this. Okay. All right, and many instructors might prefer students to be able to write this as a 5/2 times x to the, square root of x, but the power 3 here going inside, that's one way. Okay, or some other instructor expects their students to write this as x times square root of x. These are all the same answer, the same expression. All right, and I have a couple other problem in this example for everyone to try as well. All right, so let's look at part D of the example. So how about y equals, so let's leave this one for viewers to try on your own right here. So how about x squared with the cube root of x right here. Okay, so it's x squared in product with cube root of x. Okay, and so for viewer to try, so now go ahead and pause the video and calculate your own derivative right there, and then I am going to fill in the final answer. All right, so hopefully you've had your own understanding a little bit, but the work here is going to give me, so this is 7/3 times x to the, and this is, I'm talking about final answer. Okay, so 7/3 times x to the 4/3 power, and that should be your final answer. And once again, feel free to contact me either through as a comment for this video, or through the way to contact me if you are a student enrolling in my class. Okay, and let's look at some other problems. So question E. So what about when our function, how about f of x here in this case is about 1 over x to the 4th power. We got fraction, and we haven't learned any rules that handles about fraction. And so, but this kind of problem is being put within our study about the power rule. Well, there's a power, but this power is right now is in the denominator. So again, I am going to rewrite my expression. I'm not taking the derivative yet. I am going to rewrite my expression as, so this 1 over x to the 4th right here, it's a reciprocal of x to the 4th. So I can think of that also as, it's just the rule of algebra again. X to the negative 4 power. Okay? And so earlier from part C, okay, I mean part B up to C and D right there, we were realizing that the power rule also worked for the power being a rational power, but here the power itself is a negative power. Power rule works too. Okay? And so now we are ready for applying the power, but you got to be a little more cautious right here. So once again, about the power x, that's why since my very beginning problem here, since my very first problem, part A of example 1, I was writing it carefully. The original power minus 1, okay? Because sometimes if you do mental math, you dangerously, some power 4, you think that the final power is negative 3. That's dangerous. This is actually negative 4 plus 1. It's not what we want here. It's always, the rule says the power minus 1, okay? And then the original power also is multiplied in front as a coefficient. So your final happy answer here is negative 4x to the negative 5 power. I am personally fine with my students submitting answers like this, okay? But in case that you have an instructor that expects you to simplify all the way to the end, then this power of negative 5 right there, you can rewrite all that as negative 4 over x to the 5th. But going from here to here is just a matter of how well you understand your algebra. Okay, so now you feel like the power rule even got more power because it can even handle the negative power. All right, and so I'm still not done with example 1. Let's look at another problem right here. And so the worst case you can see, and this is actually not question D, this is question F. So how about y equals 1 over cube root of x. Okay, and so now for viewers with good experience in algebra, then you can already see, and along with how I'm trying to explain, the point now is that a lot of times power rule is not trivially useful yet. Okay, that's what I mean. I mean, it's not so clear right by first sight that you can apply the power rule, but we can do some algebra trick to make it look like a power, so that you can easily apply the power rule. So here I'm looking at before taking the derivative, your expression is the same as, and it's a cube root. So, well, 1 over x to the 1/3 power. And now similar to the earlier problem where we had a power in the denominator, then we can rewrite y as x to the negative 1/3. And trust me, maybe in the next couple of lectures and looking back at this thing, anyone viewing this video would be way more fluent than the number of steps I'm going through here. And so your process is going to come a lot faster in the next couple of lectures. So now you are ready for applying the power rule, dy dx. So this is your legal derivative at this point. This is not derivative yet. This is the derivative. X to the negative 1/3, but that power originally, now we're going to subtract 1 more. So negative 1/3 minus 1. And then the negative 1/3 that was originally our power, now it's going to multiply as the coefficient here. And so overall, your final answer is negative 1/3 times x to the negative 4/3. That's one way of, and this is the most direct answer right here because it just simply shows the final derivative. But like I said, in case your instructor expects more in terms of how you can simplify your work, how you can re-express your work right here in other form, then this is negative 1/3 cube root x to the 4th. That's how we're writing it. Okay, that's another way of writing that. And of course, between these two steps, you can also write it as negative 1/3 x to the 4/3 power, but in the denominator. That's another way of writing that as well. All right, so now as a bottom line, after seeing quite a few, but hopefully representative enough for the kind of problems that anyone viewing this video might run into, then we can kind of put a bottom line now. So just along with the way how I show my shorthand symbol for writing derivative, then so now anytime you have an x to the n power, okay, it's a power function, and then the problem is asking us to take the derivative. So the instruction here says find the derivative of that function as a power function. Then we already learned, and this is our famous power rule as a recap right here. So the power rule says the derivative of any power can just simply be the n from the original power now as a coefficient multiply with x raised to the n minus 1 power. Okay, so that famous power rule that we've learned now is including, so it's true for where n is any value, except actually it's true for any value where n is a real number. Okay, so you can really use, it's not only, I mean, it's just us, our human mind, a lot of time when thinking about power, we think about power 2, power 3, power 1, power 0, or maybe power negative, but we stay with the whole number, with integers. But then as we realize, even rational number work too. So x to the 1/2 power rule is going to be able to handle that as well. Okay, and even when your power is an irrational number, we don't have much application of power function where it's an irrational power, but it's also work as well. So this is really our final version of the power rule for, really it's on any value of n like that. Okay, and so now it's time to look at the other basic rule to complete our understanding. So other basic rule, but not anywhere less important. It's just me that I love to introduce the power rules before introducing these basic rules right here. But we're still in the same discussion here. We're still under that in the same lecture here. So now I will have separate videos to show you the proof, the formal proof. But here I'm just going to get straight into the actual rules and easy enough to understand. And then if you have time, you can optionally look at my other videos for seeing how these rules are being proved. And I might deliver these rules, I might post these proving videos in time for your learning or not, but it's not important. Okay? But so now, a lot of time, you have your problem as, or the function that you are taking the derivative is a function that comes from the sum of two other functions. And in your problem, you are asked to find the derivative. And that's why learning about this style of using symbols is making it, or using notation is making it a lot more convenient to communicate like that. But so once again, what I'm trying to express now is that a lot of time, you're working on a function that comes from the sums of two other functions. That's what the f of x plus g of x is all about. And then on top of that, you are asked to find the derivative. That's what this operator is indicating. this instruction is indicating. And so now this rule that I'm about to introduce guarantees that you can just simply find the separate derivative for f prime, and find a separate derivative for g, f prime and g prime. And what's going to happen between these? We're going to add them. Okay? So this is, ladies and gentlemen, we refer to this as the sum rule. Okay? The rule allows you to take the derivative of a sum. So another way of saying is that when you have, this is best applicable in a situation where you have your functions having multiple terms. This term add another term, add another term, then the sum rule allows you, as the impactor here, allows you to find the derivative term by term. Okay, that's the way how I see it. And of course, we will get we will get into that later on as we go along. But now that's what the sum rule is. And so the reason I was holding on to putting up any example is because I want to finish up with this idea first, and then we're gonna put it all together in some good examples. But now, so likewise, similar to, sometimes you're working with function that comes from the sum of two other functions. Then there are other times that the function that you're working with comes from the difference as a difference of some two other functions. And then you are asked to find the derivative of the overall function. And so now the rule I'm about to introduce here, another rule here is indicating that, is guaranteeing that you can just simply find the separate derivative for f and find also the separate derivative for g and subtract the two in the order how they started out. So in the beginning it was f minus g. So here when you take the two derivatives, it's also f prime minus g prime. Okay, but this rule here, so the rule that we've learned just previously is called the sum rule. So here, this rule that we just now learned is focused on a difference. So yes, we call this, it's the difference. Difference rule. All right. And so in that way, many textbooks deliver the rules, the sum rule and the difference rule together as one rule. So I'm just going to point it out in case you won't be shocked when you read some textbooks out there. But so sum rule and difference rule, a lot of time in some textbooks, or maybe in some a little more advanced textbook, being written in this way right here. Anytime that you have your function that comes from either a sum or as a difference, so plus and minus here means you can have the relationship being the sum or the difference between some two other functions. That's why I was saying a little bit earlier that we're looking at two different terms like that, and you are asked to find the derivative. Then the sum or difference rule together combined. It's saying that all you do is just easily find the two separate derivatives, f prime and g prime. And depending on how they started at first, if it was a plus, then we add the two little derivatives. If it's a minus, we're going to subtract the two little derivatives in the same order how they started out with. Okay, so this is another combined version between sum and difference rule like that. Okay, sum and difference. Rule. All right, and so now at this point we are ready for some good action. I mean, even though it's just some small example, but let's do some example. Okay, and so let's look at example 2 right here, but only a short one. All right, let's say find f prime of x, or dy dx. Okay, right? And so part A, our function is going to be, how about x to the 5th plus x to the 4th. Okay. And so this function that we have right here, and I have to also make clear that this is just a naming choice. In our formula, we already use f and g. Okay, f plus g, take the derivative is f prime plus g prime. So, but this f is not the same as that f. It's just the idea of, the representative idea that, your function comes from two terms. So this is a little f, and this is another little g right there. But this, if you call this f to associate with your sums or difference rule, then do not confuse this one with your main function here being f. Okay, I just want to clear that out. But so you have two separate terms, first term and second term. So if now we're finding the derivative of our main function, then that's just the same as x to the 5th plus x to the 4th, all in one function, but two terms added together. Take the derivative. Okay, and so now taking that derivative, the sum rule just now we've learned is telling us that we can now find the derivative separately on x to the 5th and a derivative separately on x to the 4th. Okay, and add the two separate derivatives together. Okay, and so now again, power rule applies here. Okay, the power rule applies there and applies here. So x to the 5th now, and at this point, the power rule is only part of the work. I'm not going to be too picky anymore. It's going to be 5x to the, that power subtract by 1/4. That's how we can move fast. Plus, this becomes 4x to the, now power 4 minus 1/3. Okay, that's your final derivative. Okay, so we apply straight out from the rule right there, the sum rule. So how about another problem as part B of the example we're currently in, example 2, but now part B. So let's look at how about q of x. How's that? Now I'm getting tired of naming f and g and all that. So let's save f and g for the little part in your the formula. And so q of x is some function, right? And we're looking at, how about x to the 99 power minus x to the 80 power. Okay, and so two terms, but this time, or two separate functions. This is some function f, this is some function g. They are connected by the difference. And so q prime that we're looking for is really the derivative on this difference, x to the 99 minus x to the 80, but we take the overall derivative. The difference rule, that's what we need to use this time, is saying that you can find two separate derivatives, x to the 99, take the derivative, x to the 80, take the derivative, and subtract the two derivatives. Our final answer. Again, each one of these, this is where, and these are where power rules apply. The power rule is applied here. So 99, the original power comes down as coefficient in front, x to the 99 minus 1, which is 98 now. Okay. X to the 80, original power is 80. Now it comes down after derivative, 80 as a coefficient in front, x to the 80 minus 1, 79. Subtract the two separate powers. You've got another derivative. Okay, and so what if it's, a function is more than two terms? What if your function is more than two terms? So let's say I'm going to call that part C before we're done with this particular example 2 right here. But how about P of x, capital P of x is, I'm running out of creativity here, but how about x to the 6 minus x to the 3rd power plus x squared. Okay, and even minus 3. I'm just, see, anything you've learned prior to this point applies here. Okay, so P prime of x our challenge here is the whole lengthy multiple terms here, x to the 6 minus x to the third plus x squared minus 3 right here. We have to consider the entire lengthy expression here. There's difference, there's sum here, there's difference there. We have to take an overall derivative. But see, the whole point of sum and difference now when we apply them in a combined situation like this, it's all about, it's allowing us that flexibility to be able to find derivative term by term. Okay, so first term, we're going to find a separate derivative for the first term, another separate derivative for the middle term, the second term actually, and x squared gets another derivative for that, and 3. Remind yourself, it's a constant. Take the derivative, and these signs right here now going to appear as how they started out in the beginning. So difference here, sum there, and difference here. Okay, but the first term gives me the derivative 6x to the 6 minus 1 power 5 minus, now x cubed, the power here is 3 in the derivative, 3x, 3 minus 1 power 2. Okay, and now it's a sum between these plus, now we're looking at 2 times x. Okay, x to the power 1 namely, but we have our right to skip the power when it's power 1, minus, derivative of a constant. We've learned that previously. This is a 0, and there's no need to write a minus 0. We are done with our final derivative. Okay, and that's how we apply the sum and difference rule. So how about after this example, let me introduce one more rules, and surprisingly we're going to have a huge opening door for us being able to do a lot more problems in that, to be able to handle much more problems. So let me hold on to doing examples. Let's look at one more rule. All right, so now a lot of times the function that you are taking the derivative is in the form of a sum function, and it has a constant coefficient. Surprisingly, the idea is very simple, but we just have to formalize it and make it into a formal rule right there. And trust me, maybe even before I start introducing this, some of you already had in mind what it should be. But it's just math. We have to formalize every single thing and make it into either a rule or a formula. So here, what we see here is that a lot of time you have to find derivative of something that, some function, and has a coefficient in front. Say like a 5x squared. This is the x squared as a function, but 5 is a constant coefficient. So function is here, coefficient is there as a c. That's what I'm trying to say right there. Okay, and so now there will be a lot of times that you are asked to find the derivative of a function that comes with a coefficient, a constant coefficient in front. And so this simple rule is indicating that, hey, if we're running into a situation like that, simply just find the derivative on the main function, f prime. Then multiply with the constant coefficient right there. Okay? So in other words, that constant coefficient doesn't have to get the derivative. Okay, and this rule right here, yes, you can name it however you want. I would just refer to that as the derivative of a constant coefficient. How about derivative? Okay, derivative. Okay, for constants. I shouldn't write it that way. This is derivative for constants, but not just any constant. These are constant coefficient. All right. So what is so useful about this rule over here. Let me bring up some quick little example. Now this one here shouldn't be part of our formal examples yet, and I wouldn't call this example 3, but just a little small example to demonstrate the idea here. So if you're looking at how about 5 times x to the 4th power, this is one function, but this time the main function I recognize is the x to the 4th. Okay, and it has a coefficient 5 in front. And now let's say we need to find the derivative. Okay, so now with the rule about how we can handle a constant coefficient, then we know that all we have to do is simply take the derivative of x to the 4th. That's the main one we have to concern about. And once we're done with that, the constant coefficient 5 just remains there and multiplied all together. And so x to the 4th, after taking the derivative, will give you some extra coefficient. So it's all going to account together. So x to the 4th is going to give you 4x, well, power of 4 originally, so now 4 minus 1, 4x to the 3rd power, and all together. See? So constant coefficient rule says now you're just going to multiply the original constant coefficient back. And so your final derivative now is 20x to the 3rd power. And once again, trust me, because right now I'm the instructor and you know, delivering a lecture online in these days. You know, I completely lack out all that face-to-face interaction between instructor and students. And so, you know, it looks like it takes forever to explain one concept right there, but once you're fluent, these things are gonna go even half a second. Okay? All right, so now after the sum and difference rule, this is the 3rd rule, and really that's really all I have to deliver in this lecture. Let's just now have fun applying these. Okay, so let me put that the rule we've just learned there. So constant coefficient that multiplied to a function, and when we're asked to find the derivative, we can just simply find the separate derivative and multiply the constant coefficient back. That's all it needs right there. And we refer to that as, okay, this is one other basic rule, but very useful. Okay, derivative of a constant coefficient. Okay, so now let's dive into some more examples. So now I am going to continue with example 3 right here. All right, so let's find again f prime of x or dy dx. And now at this point, allow me to do a little slightly advanced, more advanced problem. I'm not going to beat around with the very elementary function, like, you know, just like the 5x to the 3rd power, similar to the one we have done earlier. This is way too easy. So let's, in this example 3, let's bring up problems that are, how about combine all the rules we've done here, and along these steps right here, you're going to recognize where I apply all that new rule we've just learned not too long ago. Okay, and so all right, so question A. How about your function f of x here is x to the 6 minus 1/2 x to the 4th plus 3x squared minus 5. Okay, and I apologize for writing the prime here. There shouldn't be that prime, it's just f of x. Okay, and so we have our function here. It's a polynomial, and each one of these terms is a power of x. So that's where, when you take any of these derivative, it's going to apply the power rule. But in the end, the entire picture, as an overall picture here, the entire problem has 4 terms. 1, 2, 3, 4. They got difference between these two terms, sum between these two terms, and difference between these two last terms. Okay, so sum and difference rule applied continuously here. And some of these terms got a coefficient. And as a matter of fact, we don't see any coefficient here. Not true. Coefficient 1 is here. Okay, and so f prime now it's time to really find f prime. Okay, so f prime of x is x to the all that here. I'm just gonna put up some general instruction. We're gonna find an overall power of the whole thing like this. And now sum and difference rule, I'm using that interchangeably together at the same time. And so x to the 6 as one separate power minus 1/2 x to the 4th, I mean not separate power, I meant derivative. There's another separate derivative there, plus 3x squared, all that here. There's another separate derivative, minus 5, another separate derivative. So right here, instantly, I was using the combination of difference and sum rules. Okay, and now power rule immediately applies for that first one here. That gives me 6x to the 5th, and at this point, there's no need to slow anybody's thoughts down, anymore. So now I have to move a little bit cautiously here. See, 1/2, keep that there. X to the 4th, take derivative, is going to be 4x cubed. Okay, and then we're going to multiply it all together. Plus, now the 3 as a coefficient, keep that there, but multiply with the derivative of x squared is going to be 2x to the 1st power. Okay, and the last term, it's a constant. So derivative of a constant is a 0, minus 0. So our final derivative going to be 6x to the 5th. Okay, now 1/2 cancels with 4 and gives me negative 2x cubed. Okay, and then plus 3 times 2 combined together, the two factors is 6x. That's your final answer. Okay, all right, so we made it to one more example, and this one here we had fun. I hope anyone viewing this video might enjoy doing that. But the point now is that, see, and nowhere here we had to use limit definition any longer, and we had all that quick, effective solution to find derivative of a whole ugly looking thing like this. Okay, and so let's look at, how about another one. So I am going to so y equals x cubed minus 3 over x squared plus cube root of x minus 1 over square root of x. Okay, and so I put the problem, I create a problem that's even a little more challenging right there. But once again, so in here we got 1, 2, 3, and 4 terms. So and the way they look now, well, that first one is pretty trivial, and you already know or had an answer in mind, so excuse me. But any of these might not come so trivial. So let's not rush. So I'm not looking at derivative directly yet. Let's rewrite. So in my next step, it's not the step where we take derivative yet. X cubed remain the same because I didn't take the derivative yet. This thing right here, we can write it as a, see, 3 over x squared. It's a power, but in the denominator. So how about I'm going to rewrite it as 3 times x to the negative 2 power. Okay, so how does that sound for everyone? Okay, so the negative 2 now perfectly displayed its power nature of that term right there. And you got constant coefficient here with that. Okay, and then this term here, once again, another unclear term because, if anyone worry about roots, now we can get away with that. Root can be re-expressed as 1/3 power, okay? And now minus sign, minus here, and then that becomes 1 to the, see, x is the same as x to the 1/2 power, but in the denominator. So your overall expression here can be regarded as x to the negative 1/2 power. Okay, and so now our function here start out in the written form of being an equation. So now I'm going to use that symbol dy dx. So dy dx here is going to be, I am going, once again for starter, I am going to write an overall indication. X cubed minus 3x negative 2, to the power minus 2 plus x to the 1/3 power minus x to the negative 1/2 power, and I'm going to take an overall derivative. That's sort of like an indication for what the plan right now is. Okay, so now we are ready for the next step. So the derivative here. First term, sum and difference rule says, first term we can do 3x squared, and now allow me to start picking up the pace a little bit. Okay, next term is a minus. Okay, there's 3, but this x minus negative 2 becomes a negative 2x to the negative 3 power. Remind yourself that it needs to be negative 2 minus 1. Okay, and then this next term plus, okay, 1/3 as a power, that's the original power, multiply as a coefficient, x to the, now 1/3 minus 1. 1/3 minus 1 is a negative 2/3. I'm spelling it out right there so anyone viewing my video can follow along. And then minus, and then negative 1/2 as the original power. So now it's negative 1/2 is being the coefficient. Okay, but then x to the negative 1/2 minus 1. Negative 1/2 minus 1. Okay, if you're viewing along and take notes, make sure you write it down. Negative 1/2 minus 1. That gives me negative 3/2. Okay, and now we are ready for our final answer here for this in this problem. All right, so in my other board right there, then the final answer now is going to be, so our final dy dx equals, so 3x squared is the first term, easy to understand. So a little bit back on the other board right here, but so right here is minus 3, but times negative 2x to the negative 3rd power whatsoever. And so that means we're going to now switch sign to positive 6x to the negative 3 power plus 1/3 x to the negative 2/3 power, okay, and plus, okay, just like that. Again, for the other term, we had that minus, then in parentheses there was a negative right there. And so now I'm going to have plus 1/2 x to the negative 3/2 power. And we're done with another derivative problem. Okay. And so now at this point, let's look at we are actually done with example 3 here. But before I get into example 4 or the next example, in general, I need to mention one thing. So now back to that rule of the, you see, when we were taking the rule of a constant, okay, let's give it another explanation again of why this rule is true. Because I was approaching it completely, when I was proving this rule earlier, I was completely using the limit definition. But and then after that point, the rest of the discussion was all power rule and power rule and power rule and all that. So how can I see this result as part of the power rule? And so now after we've learned all the basic powers and all the basic rules and as well as the power rules right here. Here's how we can see it. This. Any constant, okay, if our function, and now we're attempting to find the derivative, but look more closely into our function. Being a constant function means it's a c times 1, okay, so I'm not doing the derivative yet, so this prime symbol is still hanging out there, but I'm trying to really express that c is the same as c times 1, and 1 here is famously known for, we can think of 1 as any x power but raised to the 0 power. That's how it is, okay? And so x to the 0 power multiplied with a coefficient. So all of a sudden, this c now, in the beginning it was our constant. Now we can purposely see that as a constant coefficient to a 0th power of x, okay? And so now with the rule we've just learned about derivative of a constant coefficient, then this thing becomes, we keep the c there. This gives me 0 multiplied as a coefficient times x to the 0 minus 1 is a negative 1. That's our derivative. But regardless of what power that is, regardless of what value c that is, the overall answer due to that 0, the overall answer is 0. And that is, once again, the reason why, I give a second proof of why, our derivative of a constant function is a 0. Straight out just that. Okay. And so, let's now look into our example 4 over here, where I'm going to be able to show a little more advanced level. So you can see that as I introduce these examples, I bring in more challenge as the number of examples increases. So we're still doing similar work. Find f prime of x, or sometimes we can refer to that as dy dx. Here comes our first function. So after we've had a lot of experience with the earlier problems, how about we're going to look at something like this. Our function, and maybe it's just one problem that we need, and that's really it, and you will get a good hang of it. Anyone viewing this video is going to have a good hang of it. But how about our function is x to the 4th power minus 3 x squared plus 5, okay, but over a x squared, for example. Okay, so this is how we can even be a little more flexible, because in the end we still haven't learned too many rules yet. We only learned the power rule and about 3 other basic rules, plus the rules for the constants. So that's about 4 rules, 4 nice rules we've learned up to this point right here, the way to find derivatives effectively and efficiently on any function. So this function now, you are asked to find the derivative of this function, but look at the way how it is. It's got crazy things going on. There's a polynomial in the numerator, and there's a denominator here, and the overall thing is a quotient. Well, sadly, we have not learned up to this video lecture right here. We have not learned any quotient rule yet, any derivative rule that handles directly a quotient. And so, in that way, we can be a little clever. Algebra is the key again. I am sorry for keep saying this, but you have to review your algebra, and you got to constantly practice on your algebra. You got to get that going before you can get any further. Otherwise, at some point in your calculus study, you're going to have to fight really hard. Okay? And so, what does the algebra help about this? What can the algebra help about this? So I'm not talking about finding derivative yet. We're just going to use the algebra and make things, bring things into a level that we can handle the problem. Well, the good news right now is the entire denominator has only one term. So we can break that into 3 separate little fractions. X to the 4th over x squared minus 3x squared over x squared. That's what algebraically allowed it, plus x to the 5 over x squared. Now we break the whole expression into 3 separate terms, and let's do a little cancellation. X to the 4th over x squared, and I'm not doing any derivative yet either. F of x at this point is rewritten as first term gives me x squared, middle term gives me 3 constant, last term is a little quotient 5 over x squared, but I can now rewrite that as 5x to the minus 2 power. Okay, and now for the derivative. Now we are ready for taking the derivative. All that x squared minus 3 plus 5x to the negative 2 power. The whole thing is now ready for a derivative work. I am going to again move over to my other board, but leave me about a minute to erase. All right, so now term by term, then my final derivative is going to look as following. 2x is my first term. Middle term is a 0. Okay, last term becomes well, let's keep that 5 there, minus 2x to the negative 3. Remind yourself that in the beginning power right here, it was a negative power, but now when you take that derivative, it's minus 2 minus 1. Okay, and so here in this case, minus 2 minus 1 gives me a final power negative 3. So as your overall answer, f prime of x equals 2x. There's no need to write minus 0 anymore. Minus 10x to the negative 3. We are done with that problem. Okay. And so I just quickly had in mind now a thought. So this was not originally part of the lesson plan right here, but maybe I should also include that in this video lecture in case any of my students or any viewer want to know. So how about the problem we just finished? I initially only planned to do one problem in this example 4, but let's look at another one. So how about part B right here? Okay, we got y equals x squared, okay, minus 4x, and we're dividing that by a square root of x. How's that? Okay. So now definitely we have to rewrite something. First of all, the square root in the denominator can be understood as x to the 1/2 power. Now x squared in the numerator minus 4x. Okay. And I'm not doing anything with the calculus, with the derivative yet. Okay. I'm just simply getting my expression be eventually brought to a point where I can apply the rules I've learned so far. So we didn't learn any quotient rule yet, so now I'm going to have to break this quotient. But the huge plus at this point is I have already successfully turned that square root into a power 1/2 in the denominator. Okay, and so now similar work, and I'm still not getting any derivative work yet. First term is going to be x squared over x to the 1/2 power minus 4x over x to the 1/2 power. Okay, and so we can cancel something, but now the reason I brought this up, it's more my other intention is to reveal a little bit of algebra. Now when you clear this out right here, when you simplify this, anyone viewing this video, when you're attempting to simplify this, then it's the same as x, but the power 2 minus 1/2. It's the way how we got common base here and two different powers in a quotient, and so it's 2 minus 1/2, and that gives me as an overall power x to the power 3/2. Okay, and then minus now 4, with that x here cancel with the x to the 1/2, so it's 4 times x to the 1 minus 1/2, and 1 minus 1/2 is a 1/2. So your overall power here is to the 1/2. So your expression now turns into something a lot nicer where you can handle the derivative much easier. Okay, so dy dx. Again on my other board. All right. So dy dx is going to be x to the 3/2 power minus 4x to the 1/2. But we take an overall derivative, and so first term, x, and then right, that's the difference rule, and now that first term becomes a 3/2 times x to the 3/2 minus 1, so that gives me 1/2. Okay, and then the next term here, there's a coefficient 4 right there multiplied with our main function x to the 1/2. So I'm looking at minus 4 times here, I'm doing 1/2 times x to the 1/2 minus 1 is a negative 1/2. And so now 4 times 1/2 is cancel with 1/2 is a 2. So my final answer here is 3/2 x to the 1/2 power minus 2x to the negative 1/2. And we are done with our final derivative for this problem. Okay, and so we have made it through all of the examples in our study here, and particularly in this lecture about the power rules, and along with the other basic rules that we learned, and the so useful things about these 4 rules we've learned in this lecture here is they open a big door for us to all of a sudden we feel like we have done a lot of derivatives today. And no more limit definition. We don't have to go through and worry about if we simplify it incorrectly. Well, you still have to simplify, but for different purpose right there. Okay? And so before I close down this lecture right here, then there's one last thing I have to point out in case anyone is going to be confused between the two. But so all of the functions we have done at this point, let's say we have seen x to the 6th power. So this is how I call that. It's a power function. Okay, this is a power function, but more particularly power of x. Okay, but then there's a huge difference between x to the 6 and 6 to the x. Okay, you must have learned about this kind of function as well. This function is not a power function. This is called an exponential function. Okay, so you have seen the function back in algebra, but you have seen it only in terms of what the graph looks like. But as far as doing the derivative, please don't do this. Well, for this, when you find the derivative, x to the 6th, take the derivative. Yes, the answer is 6x to the 5th, the power minus 1, and we get that and all that. And the reason I have to mention, because it's easy to get confused in a sense that this thing here right here does have some exponent form. This is also exponents, another way of calling that. So I have students in my past quarter easily make this mistake. The derivative of of 6 to the x equals x, the power brought down in front, times 6 to the x minus 1. Okay, I understand that anyone after learning the power rule is so in love with the power rule, but unfortunately this is not where we can apply the power rule. So doing the derivative for exponential function this way is completely off the hook right there. I will get to exponential function in a later discussion, in a later lecture, but this lecture here, let's save exponential function for later. Okay, I only want to make sure that it's your responsibility to clearly distinguish where it is to be a power function and where it is to be exponential function. So don't use power rule for exponential function.